Next problem based on the displacement current is a 100 ohm resistance and a capacitor of 100 ohm reactance are connected in series across the 220 volt source. When the capacitor is 50% charges, the peak value of the displacement current is. We are given that source is having the voltage equal to 220 volt and this voltage is RMS value. So Vrms is 220 volt. And we know that in a circuit having the capacitor, displacement current will be equal to the conduction current and it will be equal to Vrms divided by impedance of the circuit. The circuit contains resistor and capacitor. So impedance of the circuit will be equal to the R square plus XC square. XC is the capacitive reactance of the capacitor. And R is given 100 ohm. XC is given 100 ohm. So it will be equal to square root of 100 square plus 100 square. So it will be 100 root 2. So it will be 220 divided by 100 root 2 ampere. And this is the displacement current RMS value. To have the peak value, we have to multiply the RMS value with root 2. So we will have it is equal to root 2 into 220 by 100 root 2 ampere. Root 2 get cancelled and it will be 2.2 ampere. Hence option A is the correct option. Next question is a parallel plate capacitor of capacitance 20 microfarad is being charged by a continuous voltage source whose potential is changing at a rate of 3 volt per second. The conduction current through the connecting wire and the displacement current through the plate of capacitor would be respectively. We know that circuit containing the capacitor conduction current through the wire will be equal to the displacement current through the plate of the capacitor and it will be equal to the rate of flow of charge. And we know the charge in the capacitor is the product of capacitance and the potential difference across the plates. So we can write it as differential of CV. Capacitance of the capacitor is constant, so it is taken out of the differential, so it will be C into dV by dt. We are given that capacitance of the capacitor is 20 microfarad and rate of change of voltage is 3 volt per second. So on multiplying we will have 60 microampere. So conduction current and displacement currents are 60 microampere. Hence option C is the correct option. Next question is, out of the following options, which one can be used to produce the propagating electromagnetic wave? Options are a chargeless particle, an accelerating charge, a charge moving at constant velocity, and a stationary charge. We have already discussed that a stationary charge can produce only electric field, while the charge moving with constant velocity can produce electric field and magnetic field, both. And the accelerating charge can produce electric field, magnetic field and electromagnetic waves. While the chargeless particle cannot create the electric field or magnetic field or electromagnetic wave. So option B is the correct option. Next question is, a radiation of energy E falls normally on a perfectly reflecting surface. The momentum transferred to the surface is. It is given that energy of radiation is E. So momentum associated with the radiation will be equal to E by C. We can symbolize this by P. The radiation fall on a surface and after striking it reflect back with same momentum because surface is perfectly reflecting. So we can write if Pi is minus E by C because downward direction is taken negative, so final momentum will be E by C because finally radiation is coming out of the surface. So change in momentum will be equal to final minus initial. This is equal to E by C minus E by C. So net change in momentum will be 2E by C. This is the change in momentum of the radiation same change in momentum is transferred to the surface. So we can say momentum transfer to the surface will be 2E by c from the conservation law of momentum. Option B is the correct option. Next question is, in free space the energy of electromagnetic wave in electric field is UE and in magnetic field is UB. Then we have to check the relation between them. We know that energy in electric field UE is half epsilon naught E square into V, where V is the volume of the space, and energy in magnetic field is 1 by 2 mu naught into V square into V. Using the UE, we will have, by multiplying numerator and denominator by mu naught, it will be mu naught epsilon naught into E square into V. We know that speed of electromagnetic wave in free space is c, which is equal to 1 by root mu naught epsilon naught. So we can write that mu naught epsilon naught is equal to 1 by c square, and replacing in UE it will be 1 by 2 mu naught into 1 by c square into E square into V. So it will be equal to 1 by 2 mu naught E by c whole square into V. Also we know that speed of electromagnetic wave in free space is equal to the ratio of electric field vector and magnetic field. So we can write that E by C is equal to B. So UE becomes 1 by 2 mu naught into B square into B. So this is the formula of UB. So we can say that UE will be equal to UB. So option A is the correct option. Next question is, the RMS value of the electric field of light coming from the sun is 720 Newton per Coulomb. The average total energy density of the electromagnetic wave is. We know that energy density of electric field is 1 by 2 epsilon naught E square, and magnetic field is 1 by 2 mu naught B square, and energy density of electric field will be equal to energy density of magnetic field. So average density will be equal to the sum of energy density of electric field plus energy density of magnetic field. So it will be twice of energy density of electric field, that is 2 into half epsilon naught E square, and it is equal to epsilon naught E square. Now to find this value, we have to substitute the value of epsilon naught. This is 8.85 into 10 raised to the power minus 12 Coulomb square by Newton meter square, and then electric field, it is given that it is 720 Newton per Coulomb square. So on simplifying, it will be 8.85 into 10 to the power minus 12 into 720 square, and in terms of unit, this will be equal to Newton per meter square. Hence, on simplifying, we will have it is 4.58 into 10 to the power minus 6 Newton per meter square. Now to convert it into the unit given in the question, we will have 4.58 into 10 raised to the power minus 6, and multiplying numerator and denominator unit by meter. So Newton into meter, it is equivalent to joule. So we will have 4.58 into 10 raised to the power minus 6 joule per meter cube. Hence option A is the correct option.